A few days ago, I came across a TikTok where the user Devolo Design modeled an Oreo in Blender. The part of the video that stuck out to me was how they successfully used the logo from the cookie's Wikipedia page to build a displacement map without any extra image processing. The cleanliness of the logo inspired me to take a shot at modeling the Oreo using Polyform. However, instead of using displacement maps, I wanted to use a different technique known as signed distance fields, which will be the focus of this video. The first step in creating our Oreo begins with general image processing techniques. At a broader level, the challenge we face involves transforming the color of each pixel into a numerical value that signifies the pixel's proximity to the logo's perimeter. However, for the purposes of making a cookie, we don't actually need a mathematically perfect SDF. Instead, we only need to create a gradient to the boundary of the logo in order for the Marching Cube's algorithm to understand how to tessellate it. To achieve this, we can propagate the logo's presence by continually averaging neighboring pixel values until we've arrived to a gradient with a resolution that we're happy with. For the remainder of this video, we'll be referring to this technique of propagating values incrementally as heat diffusion. As a side note, this concept can be found in other geometry processing algorithms as well. Wolfire Games has a great write-up how they applied this concept to calculate the correct blending weights for mapping of a character's bones to the surrounding triangles in its mesh. To initialize our field for heat diffusion, we adopt a single edge detection kernel in which we look for differences in surrounding pixels to determine whether or not we're at an edge within the image. For demonstration purposes, we'll use red color values to represent positive distances and green color values to represent negative distances. If our image kernel comes across an edge, we will set the value of our cell in the field to 0. Else, if all the colors in our matrix don't have any alpha, we initialize the cell to +1 to represent content outside the logo. Conversely, if the colors contain non-zero values in the alpha channel, we'll assign the cell a value of -1 to signify it represents content inside the logo. After the initialization process, we technically already have an SDF we can use, and depending on the resolution of our mesh, we could actually stop here if we wanted to, but that'd be too easy. Now that we've initialized our field, we can create a new kernel for the heat propagation process. In this kernel, if the center of the kernel is 0, we don't do anything. So we're treating our value as the heat source, and we don't want it to change whatsoever. If the center of our kernel isn't 0, we set the current cell equal to the average of the surrounding cell values multiplied by some constant between 0 and 1. This constant serves as a method to diffuse the heat faster if desired. And that's it. We then iterate as many times as our application requires. The more you iterate, the more the border of the logo diffuses into the surrounding field at the cost of processing time. After this entire process, all we have is an SDF in 2 dimensions. In order to generate a 3D mesh, we need to come up with an extra one-dimensional SDF that we can use to act as our y-axis in our 3D SDF. Plenty of different SDFs will work, but to keep with the Oreo theme, we'll intersect the Oreo logo SDF with a flat curved cylinder to finally bring our logo into 3D space. We can then union our logo SDF with another curved cylinder to complete the top half of the cookie. Now that we've put all that work into making a mathematically perfect mesh, let's make it imperfect. We can run each component of each vertex of the mesh through a one-dimensional Perlin noise function. This by itself can cause the mesh to look spiky, depending on the frequency, so we can apply some amount of Laplacian smoothing to relax everything. We can also vary the color of the mesh subtly by passing the vertex positions into a 3D Perlin noise function. The value returned from the noise can then be used to linearly interpolate between different colors that can be applied to the vertices of the mesh. Because we're exporting the GLTF, we need to make sure to convert from sRGB color space to linear color space so that things render correctly. To introduce a more textured appearance, we can incorporate slight irregularities to the surface of the cookie by adding jitter to the normals of the mesh. This will prevent the light from bouncing off the mesh in a perfectly smooth manner, causing the mesh to appear more rough. To finish up the cookie, we can simply duplicate the wafer and flip it upside down. For the filling, we can simply create another curved cylinder and apply more Perlin noise to the vertex positions of the mesh at a lower frequency with greater amplitude. If you enjoyed this video, please consider subscribing. Everything presented here is acting as a base for the work for the next project I'm working on. All the code in this video can be found on GitHub under MIT licensing. Thank you for watching.